Okay, 6.5 is about electronegativity and bond polarity. Um, so first let's talk about electronegativity because you need to understand electronegativity to really understand and know how to do bond polarity. So electronegativity is the ability of an atom to draw the electrons it shares within another atom towards itself. I'm sorry, with another atom towards itself. It's usually within a bond. All right, so if you look on this table, fluorine has the highest electronegativity. Now, I'm not going to have you memorize numbers, or I'm really not going to give you the charts with the numbers. You just got to understand the locations. All right, atoms that get closer to fluorine are more electronegative. You see this arrow at the bottom? I guess you can't really see because um, let me move this down so that you can see the arrow. There we go. So you see how the arrow, you increase electronegativity as you go to the left on the, I'm sorry, to the right on the periodic table. And as you go up on the periodic table, you're also increasing in electronegativity. Okay, so fluorine has the highest. So when comparing atoms, like if you compare cesium versus fluorine, fluorine has a higher electronegativity. Now, there are numbers here, but you really don't really need the numbers. Like if you're comparing boron with chlorine, all right, chlorine is one spot away from fluorine. Boron is like 4 atoms away. So chlorine definitely is going to be more electronegative. Okay, so that's kind of the like the takeaway of this. The takeaway is as you get closer to fluorine, you increase in electronegativity. The one thing that I want you to kind of memorize is that hydrogen, for the most part, is equal to both boron and carbon. Okay, like I said, I'm not going to give you these numbers. I'm not going to give you this chart. I just want you to know general locations. So the further you get to the left on the periodic table, the lower the electronegativity. Lower electronegativity. As you go down, the lower. Okay, but I want you to memorize hydrogen, with the exception of, because hydrogen's kind of weird, is pretty much equal to boron and carbon. All right, because hydrogen is somewhere in the middle, but really carbon and hydrogen have relatively pretty close electronegativities. Okay, so that's the only thing I want you to memorize. Okay, so here's problems for each pair of elements. Indicate which one you expect to have a higher electronegativity. Rubidium or lithium. Lithium and rubidium are in the same group, but lithium is higher up on the table. So just knowing that, you know that lithium is going to have a higher electronegativity. Okay, if you go back, lithium is here, all right, and rubidium is here. All right. The next one is calcium and bromine. Well, I can already tell you bromine is going to have a higher one because bromine is a nonmetal. The more non-metallic it is, the higher the electronegativity. So let me write that. More non-metallic, so non-metal, more non-metallic, the higher the electronegativity. Okay, metals have very, very low electronegativities. They don't want to grab electrons. They want to get rid of electrons. Because remember, electronegativity is the ability of an atom to draw electrons to itself. Okay, so fluorine really is going to pull electrons towards itself more than any other atom. Okay, so that's the electronegativity. All right, so why is that important? Well, that tells us something about bond polarity. All right, and we're talking about covalent bonds here. Covalent. Okay. Bond polarity is if your bond is polar or nonpolar. Polar or nonpolar. Okay. The greater the difference in electronegativity, the more polar your molecule. The greater the difference. Okay. The less difference, so if you have like two of the same atoms, like here, chlorine and chlorine, chlorine and chlorine. This is a non-polar bond because they are equal in electronegativities. Both chlorine are equal, so they pull each other the same amount. It's basically like a tug of war. What we're talking about here is the pulling of the electrons in the bond of itself. Okay? Imagine if we cloned our class and we had a tug of war with the exact clone of our class. Technically, nothing would happen. The rope would stay exactly where it is because technically you would have equal amount of pull, equal amount of strength on each side. Okay? Now, imagine if two atoms that are different in electronegativities, now one atom is going to pull the electron more towards itself. This greater red area implies more electron density. So the electrons are being pulled that direction because this is the hydrogen and this is the chlorine. So this is what's called a dipole arrow, a dipole moment, a dipole arrow. Oh, that's even I couldn't read that, and I can read my horrible handwriting. Dipole. There we go. Okay, so since chlorine is more electronegative than hydrogen, again, if you look on the periodic table, let's look on the periodic table, let's erase these. All right, here's chlorine right here, one atom away from fluorine. Remember, hydrogen is right in this location. So chlorine is much closer to fluorine, and hydrogen is further away, so chlorine has more of the negative charge. Chlorine is pulling the electrons towards itself. Okay, now sodium chloride is ionic, and this is the extreme case. This isn't really bond polarity. This is the extreme case where it's an ion. You have sodium and chlorine. Chlorine is so much more electronegative, it just rips the electrons completely away from sodium, and you actually have ionic charges. So I don't really categorize this as polar or nonpolar. This is ionic. So I'm going to kind of separate these. This is kind of what we're talking about right now. This is just an extreme case of it. Okay. So if you have a different, so if you have a difference in electronegativities, you have a polar bond. If you have no difference in electronegativities, it's nonpolar. So like if I have a hydrogen-carbon bond, remember I told you I want you to memorize that these are equal to each other. So if they're equal, that would imply that this bond is nonpolar, because for the most part, they are pretty equal. Okay, so this is what I want you to understand between polar and nonpolar bonds. All right, here's some problems. If you like to do these, that's fine. But now let's talk about how you use these polar and nonpolar to now determine if a molecule is polar. Before, we're looking at bonds, like a hydrogen versus a chlorine, or a hydrogen and a carbon, or I don't know, like a nitrogen to a fluorine. Nitrogen to fluorine. Fluorine is more electronegative, so the electrons are going to be pulled towards that fluorine side. Okay, but now let's take a molecule. Let's say I have a molecule and I want to determine if the molecule is polar. What you need to do is you have to sum up all of these little arrows. It's called vector analysis. You have to sum up all of these vectors and determine if they cancel each other out or if they don't cancel each other out. Okay, and it's pretty simple. It's pretty straightforward. Okay, imagine I have CO2. Now, part of this is you have to draw it in the correct geometry. CO2 looks like this. Okay, that's the structure of CO2. Oxygen is more electronegative than carbon. Okay, how do I know that? Look at the periodic table, and you can see that oxygen is closer to fluorine than carbon is. Doesn't matter the numbers. Don't worry about the numbers. Okay, so oxygen is going to pull electrons this way, all right, and this oxygen is going to pull electrons this way. Now imagine I have a particle and I'm trying to move it this way and that way at the same speed and the same strength and everything. What's going to happen with that particle? Nothing. It's not going to go anywhere. These arrows cancel each other out. This is what vector analysis is. So therefore, this whole molecule is nonpolar. Notice I have polar bonds. This is polar. This is polar. But the whole thing added up is nonpolar. Okay, that's the difference between the molecule and the bond. Okay, so you have this vector analysis and they cancel each other out. Okay, let's say I have BF3, for example. BF3, remember, is a trigonoplanar molecule, and I have an arrow that's pulling that way, an arrow that's pulling that way, and an arrow that's pulling that way. Okay, these all cancel each other out. Okay, basically, if you have arrows in a molecule and you have all the same atoms, it's going to be nonpolar. So since they all cancel each other out, it's nonpolar. Okay, if you have C, let's say you have a carbon with 4 chlorines on it. I have a pull there, I have a pull there, I have a pull there, I have a pull there. These all cancel each other out. So this is nonpolar. All right, let's look at it. Let's look at this one. Let's say this is a fluorine and these are all hydrogens. Okay. But remember I told you carbon and hydrogen really are equal in polarity, so these kind of cancel each other out. I don't really have arrows here. I really just have an arrow right there. The fluorine is more electronegative. So since nothing is canceling out this arrow, guess what? This molecule now is a polar molecule. Okay? So that's how you determine if the molecule is polar, is by adding up the sum of all of the polar dipoles. But just to make it easy, if you have, if every atom on your molecule is the same, then you pretty much have nonpolar. As long as you have no lone pairs, you can't have lone pairs on it. Okay, so just do the vector analysis and determine if everything cancels out. All right, and here's some practice problems. You can do these on your own, but here's a perfect example. These are going to cancel each other out. Okay, because you have all the same three groups. Notice in this case, yeah, I have all the same groups, but I also have a lone pair. So this is in a trigonal planar molecule. I'm sorry, a trigonal pyramidal molecule. Okay, with a lone pair here. These arrows don't cancel each other out. So this is going to be a polar molecule. Okay, so if you determine that the electron group is tetrahedral, you have to have 4 equal groups. If you have any less than what there should be, then it's going to be a polar molecule. Okay, so hopefully this makes sense, and we'll talk about it when we get to class some more. We're going to pause here, and then when we come back, we will do section 6.6, which is intermolecular forces, which there's a good chance you have learned this in a biology class or another class.